Post-processing heat treatment of LPBF 316L steel, influence on microstructure properties evolution. This study tested different heat treatments on 3D printed stainless steel, 316L, to see how to make it stronger, more flexible, and more corrosion resistant. The steel is very strong right after printing but can be brittle. Heating it to moderate temperatures, 900 to 1050 degrees C, makes it much more flexible and shock absorbent while reducing its strength. However, heating it too much, 1200 degrees Celsius, makes it weaker and more prone to corrosion. Another method involved slightly bending the printed steel first, prestraining, to make it stronger, and then heating it. This two-step process created a good mix of high strength and flexibility. In short, the best properties aren't achieved by simply heating the printed part. Instead, the steel is either best used straight after printing or after the prestraining and heating process, as these methods provide a superior balance of strength, ductility, and toughness for practical applications. Introduction. This research focuses on improving 316L stainless steel made by a common 3D printing method, laser powder bed fusion. While this printing technique allows for complex designs, the resulting metal can have internal stresses and a unique microscopic structure that makes its properties unpredictable for critical uses in industries like aerospace and medical. The study investigates a standard solution, heat treating the printed metal at high temperatures, 900 to 1200 degrees C, to see if it can reliably enhance the steel's strength, flexibility, and corrosion resistance. It also tests a novel two-step method, first slightly deforming the metal to make it stronger, and then heat treating it to try and regain some flexibility. A key goal was to settle conflicting reports on whether heat treatment helps or harms the material's performance. The research provides a comprehensive analysis, examining not just strength but also impact resistance at room and freezing temperatures, corrosion behavior, and the microscopic changes responsible. The findings aim to provide clear, practical guidelines for engineers on how to best treat 3D printed 316L stainless steel after printing, ensuring it is strong, durable, and reliable enough for demanding real-world applications. Conclusions. This study investigated how to improve the properties of 3D printed 316L stainless steel. The metal is very strong right after printing but can be brittle. We found that simply heating it at high temperatures, 900 to 1200 degrees C, is not the best solution. While this heat treatment makes the metal's internal structure more uniform, it creates a trade-off: it becomes less strong and much less resistant to corrosion. The highest temperature, 1200 degrees Celsius, causes the most severe damage to its corrosion resistance and flexibility. A more effective method is a two-step process. 1. Light deformation. First, we slightly bend or deform the printed steel. This makes it significantly stronger, though less flexible. 2. Precise annealing. Then, we heat it at a specific temperature, 1050 degrees Celsius. This carefully restores some flexibility while retaining much of the new strength, resulting in an excellent overall combination of strength and ductility. In conclusion, high-temperature heat treatment alone often weakens the steel's most valuable properties. For the best performance, the 3D printed steel should either be used in its as-printed state or undergo the two-step strengthening and annealing process we developed. This provides a superior balance of strength, flexibility, and durability for engineering applications. This important article is authored by the following scientists: Thank you for watching this video. Please subscribe to our channel BP International to watch more videos in the fields of science, technology and medicine.